Hello and welcome to this segment on using techniques of calculus to graph a function. This is Professor Rosenthal, and our learning outcomes for today are learning how f prime, the first derivative of a function, and f double prime, the second derivative, shape the graph of a given function f of x. So how do derivatives impact the graph of a function? Can we use the derivative first and second to determine the actual shape of the function? We're also going to learn to pinpoint the relative maximums and minimums, as well as intervals of increase and decrease for a given function, again using calculus. And finally, we'll also look at inflection points and intervals of concavity. Where is a function concave up or concave down? And let me not forget, in the second segment of this lesson, we will also look at absolute maximum and absolute minimum and how that differs from finding a relative maximum and relative minimum. So let's get started. And before we look at any equations, I'd like for us to take a look at this general graph and then understand, what does it look like when a graph is rising or falling? Because many times we're going to try to pinpoint those intervals. But let's first look at this example where we know where the twists and turns are happening. And we're just asked, for example, where is this function increasing and where is it decreasing? And then what are the relative maximums and minimums of this function? So as you go from left to right, if the graph is rising, it's increasing, and we always give the answer in terms of intervals over the x-axis. So f is increasing on, so for example, this function is increasing in this segment. It's also rising or increasing in this segment. And look over to the x values. So the x values for this first piece was anywhere from 0 to a. So it's increasing over the interval from 0 to a, but it's also increasing over the interval from b to c along the x-axis. And where does it decrease? Pretty much everywhere else. So on this left side of the y-axis, the graph, as you go from left to right, it is falling. So that's negative infinity to 0. And also, it is decreasing on this interval here, all the green areas now. So from here to here, that is a to b, and as well as from c to infinity, this graph is decreasing. So again, the intervals are stated in terms of values over the x-axis. Like it is falling over here. It keeps going in that direction, right? So our answer is over the x-axis from c to infinity as we go in that direction. So over the x values from c to infinity, this graph is decreasing. Where are the relative maximums and minimums of this graph? Okay, so those are locally the highest or the lowest points. So for example, right here we have a local maximum, right here a local minimum, and right there a local maximum as well. So also known as relative maximum. So at x equals to a and x equals to c, we have relative maximums. And relative minimum we have at x is equal to b. We have a relative minimum. What about absolute max and absolute min? These are the highest points on the entire graph, not locally, but for the entire graph, absolute highest point. So we can see the point C here is the absolute highest point. So that's absolute maximum at x equals to c. But does this graph attain an absolute minimum? Can you pinpoint, like, it is at this point that the lowest point on this graph is obtained? And the answer is no, because notice these arrows, this graph keeps going lower and lower. Same thing over here. So it looks like there is no absolute lowest point on this graph. So absolute minimum does not exist on this graph. And also another question here is, over which type of points did f of x change from increasing to decreasing or vice versa? So notice it was decreasing here, started increasing there. That's a point of discontinuity. That was an asymptote there. So over discontinuity, f can change from increasing to decreasing or vice versa. And where else did it change? So a point like this, it was rising up to a and then falling afterwards, right? So at a point a, notice at point a, that's where you have basically slope equals 0. So it changed across a point where slope equals 0. And also it changed at a point like this one. This is actually a point where it's a sharp turn like this. sharp corner, we say that the derivative is not defined because, like, are you going to go with this slope of that part or this slope or that part? And basically we say that this slope does not exist. So the derivative does not exist at a sharp corner like that. So we're noticing a few types of points where the graph is turning from rising to falling or vice versa. And those points are, first of all, points of discontinuity, points where slope is 0, and points where slope is undefined. This is going to be important as we're given an equation and we're going to try to determine how to locate the maximums and minimums, intervals of increase and decrease. So we're going to have to figure out, the point A, the point B, what are those numerically speaking? And noticing the observations we made right now is going to make our life easier in the problems when we are given the analytical function, the equation for the function. But before we go to the actual equation, one more observation, this time about concavity and inflection points. Here our question is, over which intervals is the graph concave up? Where is it concave down? And over which points did the concavity of the graph change? Okay, so we see that over here is concave up, the first interval, from -infinity to 0. Then from 0 to the point x equals a, it's concave down. Then from a to b, approximately, the graph is concave up. Between b and c, again, it turns inwards, it's concave down again. And between c and infinity, the graph turns slightly upwards, it's concave up again. So we have to give the intervals of where it's concave up. Again, these intervals are typically provided over the x values. So I'm going to first go over them again in green. So this was one of the regions. Look at the shadow over the x-axis from where to where is that happening between -infinity and 0. So it's concave up over that interval. And also it's concave up over this interval, right? And if you look over the x-axis, that's between a and b. And finally, between x equals c to infinity, again, this graph is concave up. So between a and b, c to infinity are the other two intervals. And where is it concave down? Everywhere else. That's from 0 to a and b to c. So those are the intervals where it's concave down. And what are the inflection points? And inflection points are points where the concavity of a graph changes, where the function is well defined, where it's continuous over that point and concavity changes. So for example, this point right here is an inflection point, x equals to a, and this point right here, x equals b, and also this point right here, x equals c. So the inflection points are, for this problem, x equals a, b, and c. So trying to accumulate everything we've observed so far, all this knowledge, before we go to actual rules, and the rules will help us then solve the actual problems. So suppose we have a situation like this. We have a graph y equals f of x, and notice that this graph is rising over the interval from -infinity to a. The graph is rising, right? So f is increasing. What can you tell me about the first derivative? While this graph is rising, look at the first derivative, which is the slope of the tangent line. The slope of the tangent line will always be positive, right? So while the graph is rising, is f prime greater than 0 or less than 0? Our answer is it's greater than 0. Slopes are always positive while it's rising. And between a to infinity, this graph is decreasing. And what can you tell me about the slope of the tangent lines in that segment? So they're all negative, right? Slope of the tangent line, or f prime, is always negative. Slopes are negative. So remember that this is going to be part of our rules that we're going to come up with in a little bit. When f is increasing, first derivative is positive. When f is decreasing, first derivative is negative. In addition, look at this graph. This graph is concave up. When it's concave up, if you look at the tangent lines and the slope of the tangent lines, like in this situation, not only they're positive, but they're getting steeper, right? So here, this was the slope. This is our tangent line. Here, it was even steeper. If you go a bit further up, it'll be even more steep than the previous one. So when a graph is concave up, slopes are increasing. Slopes of the tangent line, or the slopes of the graph along this graph. So slope is the same as f prime, right? So I can say that f prime is increasing along this graph as we move from left to right. And if something is increasing, if a quantity is increasing, what can you tell me about its derivative? Because notice over here, if a quantity is increasing, its derivative is greater than 0, right? So here, a quantity is increasing. That quantity happens to be this. So its derivative should be greater than 0. So take the derivative of this, which is f double prime, and that should be greater than 0. So f double prime is greater than 0. So here's what we've noticed. In a concave up graph, the second derivative is greater than 0. And you can follow a similar argument for a concave down graph. There, okay, slopes, so this one is quite steep. It's getting less steep as you go from left to right. So slopes are actually decreasing. Like if you were climbing this mountain, the beginning part is harder. Later it becomes easier to climb because it's not as steep anymore. Slopes are decreasing. And remember, slope is f prime. So f prime is decreasing. And if a quantity is decreasing, we learned up there, if a quantity is decreasing, its derivative is less than 0. That means the derivative of this is less than 0. That means f double prime is less than 0. So let's review. When a graph is concave down, typically its second derivative will be less than 0. So now we can come up with all the rules that we're going to use to solve the analytical problems. So here are some of the things that we have observed. First of all, to figure out the relative maximum, minimum, and intervals of increase and decrease, what we need to do is, first of all, we're going to set f prime equal to 0 and also look for points where f prime is undefined. These points are referred to as critical points, and they are candidates to be relative maximum or minimums. That's where the turns are likely to occur, over points where slope is 0 or where slope is undefined. Okay, so first set the derivative equal to 0, solve for x. And from that point forward, we're going to put those points, the solution to this equation, on the number line, and we'll pick test values from each of the intervals determined by those critical points. And we're going to plug them into f prime. If f prime is greater than 0, as per the slide in the previous page, we can say that f is increasing. If f prime is less than 0, that means slopes are negative. That means the graph is decreasing. On the other hand, to determine information about concavity and inflection points, so what we're going to do is we're going to set the second derivative equal to 0 and also find where second derivative is undefined. These are candidates to be inflection points. Once again, we're going to put them on the number line and find test values in between them, substitute them into f double prime. And if f double prime is greater than 0, then we're going to conclude that f is concave up as per the previous slide, right? If second derivative is greater than 0, f is concave up. On the other hand, if second derivative is negative, then f is concave down. And if the second derivative changes sign from plus to minus or minus to plus, meaning that concavity is changing from concave up to concave down or vice versa, then those points are going to be inflection points. And to complete the graph, typically we can find the y-coordinates of all the important points, and then we're going to use a sign chart for f prime and sign chart for f double prime to complete the graph. And with that, let's take a look at an example. Okay, so first we're going to solve a half example, meaning suppose we already have the sign charts created. From there, can you tell me what the graph is going to look like? And in our next example, we're going to solve a complete example where we're also going to create the sign chart ourselves based on a given equation. Okay, so let's suppose that we're given that the sign chart for first derivative f prime is minus minus plus, meaning it's negative over the first two regions you see here from negative infinity to 0 and 0 to 4, and it's positive from 4 to infinity. And suppose that the second derivative is positive from negative infinity to 0, negative from 0 to 2, and again positive from 2 to infinity. So using this information, can we get a rough picture for how the graph of f of x looks like? Now, what do we know? If f prime is negative, what does that tell us? It tells us that slopes are negative, meaning the graph is falling, right? The graph is decreasing. So it's decreasing over here, it's decreasing over there. So I might as well put one big long arrow to indicate it's decreasing over this entire region. And we're assuming that f is a polynomial function here, so it's continuous everywhere. In addition, it's f prime is positive from 4 to infinity, so the graph should be rising, right? So already we have quite a bit of information. So we know that f is decreasing from the sign chart of f prime. F is decreasing from negative infinity all the way to 4. And f is increasing from 4 to infinity. And can you tell me where there's a relative maximum or relative minimum based on the pointing of the arrows? So it was decreasing and then increasing. So at x equals to 4, what do you expect to see? A relative minimum, because your arrows are like this. So you have a minimum there at x equals to 4. And it looks like there is no relative maximum for this graph. Okay, now let's look at f double prime for concavity information. Okay, so for f double prime, it's positive over the first region. Do not draw arrows here because f double prime does not tell us information about increasing, decreasing, rather about concavity. So it's concave up over the first interval. So when it's f double prime is positive, you can put, I'm going to put C up, meaning concave up. Over the second interval is concave down. I'm using CD for that abbreviation, concave down. And then over the last interval from 2 to infinity, it is concave up. So let's write it down. So f, the graph of f is concave down over the interval from 0 to 2 and concave up. So give the values over the x-axis from negative infinity to 0. Also, you can put a comma or a union symbol, comma from 2 to infinity is concave up. And where are the inflection points? This is where concavity changed direction sign, so it went from plus to minus or minus to plus. So at x equals 0 there is a inflection point, also at x equals to 2. So at x equals 0 and x equals to 2 we have inflection points. Now how can we use all of this information to give a rough picture for this graph, for this function? So the first thing we're going to use is the f prime graph. So I usually start with like dashed lines. Just this is a very rough graph. This is not the final version of the graph. So it should be falling up to 4 and rising after 4. So roughly speaking, it should be falling all the way to 4 and rising after 4. Now I don't really have all the information, so answers could vary. Like some of you could be putting your graph like this, further down, some of you putting further up, but this is just a rough shape of the graph. That's what we're after here. We're not looking for perfection or exact y coordinates. Okay, next, use the concavity information. So it should be concave up to 0. So concave, so you must follow the general pattern that's falling and rising, but also not carve the graph using concavity information. So concave up to 0 while we're going downward trend, right? And between 0 and 2, it should be following the trend of concave down. So slightly turning the other way. I even did some exaggeration there, so you can see so there's a subtle turn from up to down. And then everywhere else is concave up again, but it should follow the general pattern, reaching a minimum at 4. So this is what our polynomial function looks like. Let's label some points. At x equals to 0, there's an inflection point. At x equals to 2, there's an inflection point. At x equals to 4, there is a relative minimum. And that's what we had observed from the sign charts as well. So when you see the graph on the calculator, you might see that the graph goes very slight turn. So here I really exaggerated the turn there so you can truly see the inflection points and change in concavity, but usually this is more typical. So still, as you can see, it's concave up a little bit and then slightly down and then upwards afterwards. Okay, so our next example will be a complete example, and for that I'm going to start a new segment.